the treatment of real gases is found within the Atkins textbook. Previously, there's been a description of ideal gases and considering how ideal gases, uh, the behavior of them in various gas laws combined with kinetic molecular theory gave us this description for an ideal gas. Now, within the discussion of real gases, we're going to look at deviations from that model. I like within this description of Atkins where it's beginning to think, well, why do we need to know about this material? A lot of times students get hung up on this word ideal gas versus real gas. They view ideal as being an abstraction that can never possibly be found. And I'm going to push back on that a little bit. I think many gases are really close to having ideal behavior. The ideal gas laws, after all, they came about from observations with everyday gases under everyday conditions. If those were not the patterns that were found, those particular relationships wouldn't have been constructed that way. So it's quite possible that if we're looking for things in a very exact manner, or if we change the conditions, we will move away from that ideal behavior. But ideal shouldn't mean fictional. Um, Important one to look at within here, an important way that we can explore non-ideal behaviors with this idea of a compression factor. So we have a description for our ideal gas law. The compression factor is looking at the volume that you would experimentally measure relative to the volume that you would predict based on the ideal gas law. So if you put in your different conditions within PV equals nRT, let's do it for 1 mole. You have a particular temperature, particular pressure. Imagine that you have a box like that. And you say, okay, what is the volume supposed to be based on the ideal gas law? Okay, what is the volume when we actually experimentally measure it? That's what we're looking at with our compression factor. So now we're seeing what happens as we're looking at the same scenario and we have examples that have higher and higher pressure. Now, if we look at this right here, we see that as the pressure increases, often we initially have the compression factor decrease and then begins to increase. That tells me there must be competing factors. There can't be just one thing that always explains it. We must have something dominant in one regime and something dominant in another. So initially within here, we see as the pressure increases, the attractive forces are dominating. The attractive forces are making the apparent volume that I measure smaller than what the ideal gas law would have predicted. And after that, the second factor would be repulsions between the gas particles, which makes the volume larger than the ideal gas law would predict. So that's what's taking place in this regime. Now, when we're talking about these non-ideal behaviors, look how huge the pressure is. Okay, so this idea, well, does this happen all the time? Well, it would happen, but first of all, in my everyday experience, if I'm not in a lab experimental setting of some kind, I'm not reaching 400 ATM. Okay, so this is, I'd say, further evidence that we're usually in this regime way over here on the left-hand side of pressures that would be more like 1 ATM, like our everyday experience. That's why it's describing here in industry and in many research laboratories, gases under high pressure right here begin to fail with this. So it makes me wonder, well, what aspects of the kinetic model that are describing the ideal gas failing when I'm looking at different gases, when I'm looking at real gases? So out of these, well, which of these will I keep? Which of these will I get rid of? So first of all, it's definitely an abstraction to say that the gas particles are infinitesimally small points. They're going to have a space that they actually occupy. And also aspects here of their movement and how they interact with each other. To me, this is beginning to think about potential energy. This idea that I can have potential energy when I have attractions or repulsions between the particles. I'm going to say that these attractions dominate when the particles are close together within a few molecular diameters apart. but they would repel each other when they get too close together. I like this description here in Atkins where it's showing the relative change in potential energy if you're looking at something that's bonding versus this intermolecular attraction. How they're acting at different distances and they're a very different magnitude. So in this regime right here, this is where attractions are dominating. So I see NH3, as it dives down, it has greater attractions than something like CH4, and they all have much, much greater attractions than something like H2. As I'm thinking about my kinetic model here, how the collisions are exerting a particular pressure, how for a given pressure, they're leading to a particular volume. I'm thinking about how the particles are striking the wall, and the opportunity, if there are attractions, for those particles to be attracted to the other gas particles within the chamber. This idea that if a particle is headed towards the wall, but it is somewhat attracted back to the other gases in the chamber, that's going to lessen the pressure that it has when it strikes the wall. For a given pressure, then, this would make the volume experimentally be smaller than the ideal. If I'm getting at higher and higher pressure here, I think what comes into play is this idea about how gases are infinitesimally small points. Well, they're actually having some space that they occupy. I sort of think about this with the PhET sim. On the left right here, this is a better representation of an ideal gas. There's mainly empty space. If you compress it dramatically, well, this is now reaching a regime where non-ideal behavior becomes important. Now, to describe these, equations of state are used to describe real gases. We could start with our PV equals nRT, and we can add more and more terms. If we add more and more terms, corrective terms, we're going to get a better description of the gas. It's going to fit the experimental data better. As we add more and more complexity, it's going to do a better and better job of describing the phenomena. So we can have more and more what are called virial coefficients. The van der Waals equation right here is a description of improving our model. It is not as complete as other ones, but as Atkins notes, it's easier to interpret. So this one's helpful because it gives some insight into what's going on. Insight into accounting for both the attractions and the repulsions. There are other equations of state besides the van der Waals equation. Some of them get quite complex. But as Atkins notes, you might be able to predict the property more accurately with a more complex equation, but it doesn't give me as much insight necessarily into what's taking place at the particle level. The van der Waals equation, that's why it's helpful, because it gives us some of that insight. So the different values, A and B, within the expression, well, if you took the compressibility data and fit it, you could use that to come up with these particular parameters. If we look a little bit more closely within this, if you want to think about it mathematically, the attractive term is going to be less important when you have a large value in the denominator. If it's a very high temperature, the attractions are going to be less significant, or when the volume is quite large. Both of these, I think, are going to give us some insights into the behavior when we move on to intermolecular forces. In terms of the volume here, the main thing that's affecting the magnitude of the volume, the size is going to be the volume that it occupies. Now, here's some data for different van der Waals parameters presented in Atkins. Something we can think about if we want to analyze this within a given classification or across those. One thing I find is I got to be careful. This was some data that I had within the Brown-LeMay textbook. Krypton within Atkins right here, it seems anomalous for what he's reporting. I usually see the information that's reported here for krypton. So I'm not sure if that's a typo within that or exactly what, but it's a strange value that he's listing there. To take this and begin to make sense of it, here's a graph. So what I did was I take a graph of the volume, which would be the B, have to do with the B factor, and the attraction, which has to do with the A. So if we're looking at this and say, well, is there a correlation between the size and the attraction? Sure looks like there is. So that's one takeaway from this. It looks like when my particles are larger, it's leading to greater attractions. But I've got one outlier here. That outlier within this group is for H2O. So this is a point to discuss, well, how is H2O different than the other ones that are listed there? And that leads us to the obvious point that, okay, all these other ones are nonpolar molecules. H2O is a polar molecule, so this is a good lead-in to intermolecular forces. Another connection within this when we're looking at the behavior of gases, just this question, how do we get liquid O2? Liquid O2 is something I use in a demo when I'm looking at paramagnetic oxygen. And the way that we get it within that is we take a test tube and put it in liquid nitrogen. The O2 is now going to condense out of the atmosphere. This has some interesting implications for what the strength of the intermolecular forces would be if I'm comparing N2 and O2. But this is how I could get liquid oxygen. My point is I can put a gas into a liquid that is colder than it, and that will cause it to condense. But how do I make something like liquid helium? Liquid helium is down at 4 degrees Kelvin. What can I put that in that is colder? This whole idea of you can make something lower its temperature by putting it in another substance that is colder than it, fine. But what happens when you reach the end? What happens when you get colder than cold? You don't have anything that's colder at a lower temperature than the liquid helium. So how can you make it? This gets at this question of, does the temperature change when you expand a gas? Look at this scenario right here. I've got gas on one side, vacuum on the other, narrow tube in between. What's going to happen when I open up the stopcock between them? Well, it's going to expand to fill up both sides. In this process, does the pressure change? Does the temperature change? Well, we initially had the gas confined in one side. When we open it up, it's now occupying a larger volume. The pressure is going to go down. How about the temperature? Does the temperature change when I've opened up the stopcock here? Very interestingly, it's going to depend. For an ideal gas, there is no temperature change. But for a real gas, the temperature is affected. That's called the Joule-Thomson effect. We've seen Joule before. The Thomson here is William Thomson, aka Lord Kelvin, sort of with his, I don't know, Darth Vader look here or something. So this is the folks that are associated with this idea. Now, I'm beginning to think then, well, what would be different when I'm considering an ideal gas and a real gas for this scenario? And a crucial thing is having to do with the attractions that can take place when I have the real gas. The scenario this is describing, it's as if I'm putting gas particles on one side of the chamber. I'm going to open up the barrier in between them, and now they move across. The key thing I'm thinking about when I'm considering an ideal versus a real is in this behavior, in this region right here, when I have a relatively small volume that the gas particles are moving through. Because in that small volume, if there's the chance for attractions to be present, that's where they would be found. And this leads to the liquefaction of gases. So, as we've considered the relationship between potential and kinetic energy, we've seen that if we have an isolated system, something all by itself, if the potential energy is going up, the kinetic energy is going down. You can't have one without the other. Now, in ideal gas, it doesn't have attractions or repulsions by definition. So any potential energy there is not relevant. However, a real gas, it does have attractions, and these act when the particles are near each other. So, in terms of the liquefaction, the molecules of a real gas, they can be slowed down by making use of these particular attractions. Because then when the gas is allowed to expand, the molecules have to overcome these attractive forces. And in the process of overcoming them, we see a decrease in the temperature. Put into words here, allowing this gas that had been compressed to occupy a larger volume, it's increasing the separation between the molecules. And this is going to lower their average speed, which means a lowering of the temperature. This will take place, but you need attractive forces to be dominant in the first place. So that's why it's relevant for a real gas, but not an ideal one. This is what's described as the Joule-Thomson effect. At ordinary temperature and pressure, this is apparent for all gases, except these very smallest of ones like H2 and helium. It will work for those too, but you have to have an even lower temperature. Here's what's taking place at a particle level. So we're sending a gas through this chamber. It's at a particular pressure and temperature. It's reaching this narrow tube part. If this is an ideal gas, no big deal. There's not going to be any change to the potential energy because the potential energy is not relevant. We don't have attractions or repulsions. There's only the kinetic energy. When it goes through the narrow inlet here, it doesn't matter. It can go through and then it can simply then fill up the space on the other side. This is an isothermal expansion. It's at constant temperature. What happens though if I have real gases and the attractions can dominate? In this region here where a compression is taking place, the potential energy is going down. The molecules, they become somewhat stuck together. So their subsequent expansion, it's going to require energy. It's going to require collisions that raise their potential energy, and this will lead to a decrease in the temperature. Notice the pressure and temperature in both of these different regions. As it's leading into that narrow portion, one finds that the pressure is higher than it would be afterwards. We find that the temperature has increased as it was compressed, and then the temperature now decreases afterwards. I'm thinking about this at the particle level of as the particles are moving across, they're initially spread out. In this narrow region where a compression is taking place, they're moving to a lower potential energy as there's some attractions between them, and this is leading to a temperature increase. This idea of lower potential energy and the temperatures going up. Let's look at this description right here. So within this PhET sim here, at the bottom, we initially have two neon atoms, and this is the potential energy well that occurs when they're quite close together. So first of all, let's switch from neon to argon. Notice what happened right there. So we would say that the argon atoms are larger than the neon, so that's what is being shown here. And we would say that they can experience greater attractions. So that's leading to a deeper potential energy well that's at a somewhat larger separation. If we want to connect this back to what we just saw with our van der Waals parameter, great connection in terms of both the size and the attractions when we compare neon with argon. So let's separate those two. So this would be thought of as when they're in this space right here. The particles are far apart. Let's see what happens to the potential energy as we bring them together. Potential energy went down, potential energy came back up. The total energy is being conserved. I can't have the potential energy go down and have them stick together. They're just bouncing off each other. Because if the potential energy goes down and there is no increase in the kinetic energy, I'm not conserving the overall energy. So this idea of saying that we have a lowering of the potential energy and the temperature increases, something else must be going on. In that process, if I have the particles coming together, and let's say they collide with another particle, that subsequent particle can remove, in the form of kinetic energy, some of the energy that we have there. It leads to a net lowering that can now allow these particles to stick together. Anytime you have a lowering potential energy, there's an increase in the kinetic energy. There's an increase in the temperature. It might be with a neighboring particle, but it's got to be somewhere. That's what's taking place in this region right here. it goes through the narrow opening. Now, after the narrow opening, I'm trying to show this cluster being somewhat stuck together. Let's say now a neighboring particle collides with those. That would serve to separate these particles, move them apart more, but that's going to use up some of the kinetic energy for the particle that strikes it. Comes back to this balance between our kinetic energy and our potential energy. The collision is going to separate these compressed particles. It raises the potential energy, and crucially, it's lowering the temperature. The T2 is smaller than the T1 that we had in this compressed region. We're lowering the temperature within this. A phenomena which I think is a cool one is the idea that if you just blow on your hand with your mouth open versus if you make your lips quite narrow, it feels colder in the second case. It's coming, from your chest cavity at the same temperature, but by making it go through this narrow opening, you've cooled it down. This is consistent with what we're looking at with our different van der Waals parameters. There's this idea right here, Atkins is saying that the only exceptions that we really have are things like helium and hydrogen, which have very weak attractive forces. This is interesting. In this case, when we're taking this, and we've seen this when we're looking at its compressibility, if we're taking this one and we're actually having that region where we're compressing them and getting them closer together, we're actually increasing the potential energy because the repulsions are what are dominating in that region. Within this region, for something like helium or H2, if you have repulsions dominating, when you compress them there, the potential energy is actually going up. This is like a coiled spring. We're increasing the potential energy. So then when we have more space for them to expand, that subsequent expansion, it produces energy. The temperature is increasing. This is one of the rare occasions that we have within this class where the repulsions are actually the dominant term. Usually we're talking about attractions between matter. This would be an example, though, where the repulsions are dominant. But as Atkins notes, at a low enough temperature, every gas is described this way. And that's how you make liquid helium. You have one where you initially have some coils that you have at a lower temperature, and then you just keep cycling the gas through again and again. And within the cycling of the gas through again and again, you're lowering its temperature. So I really like your real gases as a transition from this model of an ideal gas, giving us many insights that we can now use when we think about intermolecular forces, about the factors that might be contributing to the intermolecular forces, and connecting it when we're looking at the Joule-Thomson expansion to thinking about potential energy and kinetic energy.